In this example, we will investigate and learn 3 rules for exponents that involve division. For all of these, we will go back to what exponents mean and use our understanding of that to come up with a shortcut. In part A, we have 7 to the 6th divided by 7 to the 2nd. What we want to remember is that 7 to the 6th means there are 6 7s multiplied across the top of that fraction, and there are 2 7s multiplied in the bottom. One thing we know about fractions with multiplication and division is that we can cancel a 7 out 1 for 1. For every 7 in the numerator, if there's 1 that pairs up with it in the denominator, they will cancel out and make 1s. At this point, we've canceled out all the 7s from the denominator, and we're simply left with 4 7s up in the top, which we could write as 7 to the 4th. In part B, we have x to the 5th divided by x to the 3rd. Again, x to the 5th means x times x times x times x times x, 5 x's in the top. X to the 3rd in the bottom means we have 3 x's in the bottom. Again, just like with 7s, x's can cancel out 1 for 1. And if we cancel 1 x from the bottom with a single x up in the top, 3 of those x's will cancel out, and it will leave us with 2 x's remaining up in the numerator. Our answer will be x to the 2nd. Hopefully you recognize what just happened. By pairing them up and canceling them out 1 for 1, we've essentially just subtracted 2 of the 7s from the 6 that had originally been there, leaving us with 4. We took those 5 x's, but we canceled out 3 of them, and 5 minus 3 gave us 2 remaining. The general rule that we're working with here is called the quotient rule, and the rule states, jumping to part D, if we have a to the n divided by a to the m, we get to subtract the bottom exponent from the numerator's exponent. It leaves us with a to the n minus m. Using that shortcut, we'll jump back to part C. We have 3 to the 4th, x to the 6th, y to the 5th, divided by 3 squared, x to the 4th y. When we work this example, we want to pair the 3's with the 3's, the x's with the x's, and the y's with the y's. What happens with the 3's won't influence the x's, and likewise that won't influence what happens with the y's. So looking at the 3's, 3 to the 4th divided by 3 to the 2nd would be 3 to the 4 minus 2. X to the 6th divided by x to the 4th would give us x to the 6 minus 4. And y to the 5th divided by y, you want to remember that's a 1y down there, so that gives us y to the 5 minus 1. When we simplify this, we'll end up with 3 squared times x squared times y to the 4th. And as a fairly common final step, since 3 squared can be simplified down to 9, it would be more common to write this as 9x squared y to the 4th. So the rule is, when dividing the same base, you can subtract the exponents. That's the quotient rule. On part E and F, you'll notice that E and F are the same, and the same is true with G and H. G and H happen to be the same. We're going to discover the next rule using 2 different approaches. In part E, we'll approach this using an understanding of what exponents mean. 4 to the 3rd divided by 4 to the 3rd. Well, that means I have 4 3's up in the numerator, and similarly I have 4 3's down in the denominator. And if I cancel them out 1 for 1, we'll notice that everything cancels from the numerator and from the denominator. We're left with a bunch of 1's on the top and a bunch of 1's on the bottom, and 1 over 1 is 1. On the other hand, 4 to the 3rd divided by 4 to the 3rd, we should be able to use the quotient rule we just learned. What I should be doing is subtracting the exponents, 4 to the 3 minus 3. And we know that 3 minus 3 is 0. So approaching the problem from one perspective, we get an answer of 1. Approaching it using the quotient rule, we get an exponent of 0, 4 to the 0. What this tells us is that 4 to the 0 means the same thing as 1. The rule that we're going to look at here is what we call the zero exponent rule. Let's take another look at G and H. 2x to the 6th divided by x to the 6th. This means we have a 2 times 6x's. And similarly in the bottom, we have 6x's down there as well. As we go to cancel things out 1 for 1, it's only the x's that are canceling out. But because we have the same number of x's in both the numerator and denominator, all of the x's are going to cancel out. So what we're left with is 2 times a bunch of 1's on the top divided by a bunch of 1s on the bottom, our final answer is 2. In part H, we'll approach this using the quotient rule for exponents. 2x to the 6 divided by x to the 6 tells me this should be 2 times x to the 6 minus 6. Well, 6 minus 6 is 0, and so approaching it this way, we get an answer of 2x to the 0. Again, we've started with the same expression and simplified it 2 different ways. The only way this can work is if that 2, the answer from the first side, is equal to 2x to the 0. But the only way that can be true is if 1 is equal to x to the 0. And that's basically our rule. Any non-zero number raised to the 0 power is equal to 1. 4 to the 0 is 1, and assuming x isn't 0, x to the 0 is also 1. Continuing with a few more examples of the zero exponent rule, jumping to part L as our first step here, the general rule is for any non-zero value of a to the 0 equals 1. So jumping to part I, 27 to the 0 is 1. In part J, 3w to the 0, now you need to remember, exponents only apply to what they're immediately next to, so the only thing being raised to the 0 power is the w. So w to the 0 will become 1, but 3 times 1 is 3. So 3w to the 0 is actually 3. In part K, negative 9 to the 0, again you want to remember the 0 exponent only applies to the 9, so 9 to the 0 will become 1, but it doesn't impact that negative. So our answer for part K is negative 1. This is called the zero exponent rule. Any non-zero real number raised to the 0 power is going to be equal to 1. In parts M through P, we'll investigate the third and final rule for division and exponents. Again, we'll go back to what things mean. In part M, we have the quotient x over 4 in parentheses raised to the third power. Well, we know the third power tells us that we'll have x over 4 multiplied by itself 3 times. Using our understanding of how fractions multiply, we'll multiply straight across the top. So we'll have x to the third in the top and straight across the bottom, 4 to the third down in the denominator. You'll notice in this situation that power of 3 simply got applied to the numerator and denominator. In part N, we have x to the 7th over 5y to the 9th in parentheses squared. We know that squared tells us we'll have 2 of these, x to the 7th, 5y to the 9th, multiplied by each other. So x to the 7th, 5y to the 9th. And we know when we multiply something by itself, that's really saying x to the 7th squared over 5y to the 9th squared, because we multiply the numerators together, and separately we multiply the denominators together. Using our exponent rules for multiplication, I know x to the 7th quantity squared means I'm going to multiply that 7 and 2, which will give me x to the 14th in the numerator. In the denominator, first we're going to have to apply that outer exponent of 2 to each of the factors on the inside, so we'll have 5 squared, and separately y to the 9th squared. But I know y to the 9th quantity squared means I'm going to actually multiply the 9 and the 2, and so I'll end up with y to the 18th. So our final answer here, because it tells us to leave it in exponential form, is x to the 14th over 5 squared y to the 18th. What we're looking for in these two examples is a common pattern, and what we've seen in both of them is that this outer exponent of 3 from m ended up being applied to the numerator and denominator independently, and same thing on part n. The exponent of 2 on the outside was separately applied to the numerator and the entire denominator. We were able to clean it up or simplify it a bit further in part n, but the same basic rule is happening in both situations, which brings us to part P. When you have a quotient a over b in parentheses, all raised to a power of n, you end up applying that outer exponent of n to both the numerator and the denominator. A over b quantity raised to the n power becomes a to the n over b to the n. It is important again to look back at part B and notice when we apply that to something more involved than just a single variable or a number, you do need to include those parentheses because you might end up using a different exponent rule at the same time. Now let's jump to part O and see how this works out with this expression. So our quotient is negative 3x to the 5th over 2y to the 4th in parentheses raised to the 4th power. The first thing we're going to do is apply that outer exponent of 4 to the entire numerator, and separately to the entire denominator. So up in the numerator, we'll have negative 3x to the fifth in parentheses to the fourth power, and in the denominator, 2y to the fourth in parentheses to the fourth power. We'll now apply that outer exponent using our product to a power rule, and that will give us a negative 3 to the fourth, x to the fifth to the fourth, but we know when we have powers to powers, we multiply, so x to the 20th, and in the denominator, we'll have 2 to the fourth and y to the fourth, which means we will end up multiplying those two powers, giving us y to the 16th. Again, only because it tells me to leave the answer in exponential form do I not try to simplify this a little bit further.